In this video, we will use the goodness of fit test in order to carry out what we call an independence test. And as an example, I've chosen an opinion poll here made for some political election in which you have to choose between two candidates, candidate A and B, and you also have the option of not wanting to vote for any of the candidates. And the opinion poll has been categorized into men and women. So what we would like to investigate here, you could say our null hypothesis, is that there's no significant or no difference in the preferences of men and women when it comes to this election here that the opinion poll is concerned with. So how do we carry out this test? Well, first thing is to notice that we have two different factors, if you like, two different categories. One is the candidate, or the choice, if you like, and the other one is the sex of the voter. So we can arrange these into a table like this. So you can choose, you have the choice, so to speak, to be a man or a woman, and you can choose between candidate A, B, or none of the two. And that's why we have 6 observations here. You could say 6 counts. So if you're a man, it turns out that 60 of the interviewed persons would prefer candidate A, and 78 preferred candidate B of the men, and 40 preferred none. And for the women, the numbers are 40, 85, and 55. Okay, so what we will do now is compute the totals. Here we get 100. Here we get 163, 95, 178, and 180, and the total is 358. So what we will do now is that we will compute the expected values. And you could say expected in what sense? Well, expected in the sense of the null hypothesis. If the null hypothesis is true, that there's no difference in what men and women prefer, we can argue as follows. You can see here that almost half of the interviewed persons are men, the other half is women. So we expect roughly half of the voters for candidate A to be men. So roughly 50 voters, male voters, should vote for candidate A, and roughly 50 for candidate women voters for candidate A. Because there are roughly half of the interviewed persons who are men, we should expect half of them to be on half of the candidate A voters to be men. That's kind of how the argument goes. And the same thing goes over here and here and here. Of course, we're only talking rough numbers right now because it's not exactly half the interviewed persons that are men. So if we have to do the calculation right, we would say that the expected is the percentage of the total observations which are men. This is almost 50%, but not quite, multiplied by the number of voters for candidate A. That would give us the exact expected number here. So that's something like 49.7. And in the same way we could compute, maybe I should take another color. I'll just erase these rough numbers here and switch into another color for the next one. So the expected number here is now the number of women out of the total number of observations here, multiplied by how many voted for candidate A. And what we get here is, not surprisingly, 50.3. So that's the number we expect in this category here. And we can do a third one just to show what we actually mean here, just to make a point of it. So the expected number in this category here is then 180 divided by 358 multiplied by 95. So notice that the expected number in a category is composed out of the total in the same row and the total in the same column. So these two numbers go into that expected number. This number goes into that one and this one as well. So same row, same column. That's just a way to remember it. And here we get 47.8, so that's the number that goes in here. Right, so we imagine we do this for all 6 categories. That means we have expected numbers in all of these 6 boxes here. And what we will do then is that we will compute a sum of the observed value minus the expected. Let's say the observed ith value minus the ith expected value squared divided by the ith expected value. I will do this for all 6 categories here. And you may recognize that this is actually a test statistic, the chi-squared test statistic that we're computing. So if we do that, we get a number, and in our case, it's something like 6.658. Now this number, is that an extreme number or is it an expected number? Is it kind of in the acceptance region? That's hard to tell if we don't know the distribution of this number. And it turns out that it has a chi-square distribution, which is not surprising because we named the test statistic a chi-square. But there are many different chi-squared distributions. We have to know which number of degrees of freedom the distribution has. And to begin with, we say that there are as many degrees of freedom as there are observations. And in our case, we have 1, 2, 3, 4, 5, 6 observations. You can see it over here on the graph. 6 observations. However, we did use those observations to compute the expected numbers of the hypothesized distribution here. How many parameters did we compute? How many times did we use the data to compute these expected numbers? Well, we computed this sum, this sum, this sum, this sum, this sum, and this sum. So you'd think that we've used the data 6 times, but actually we didn't have to use the data 6 times. We certainly had to use it to find this number and this number and this number and this number, but that's it, because now we have these two, so we can compute this sum here using those two numbers. We don't have to use the data again. We have what we need here to find this number here. And once we have that total here, we can find this number here by subtracting those two totals, because we know that when we sum them up, we should get 358. So really, we only used the data 4 times to get these totals. In other words, to get these expected values. So that means we reduce the number of degrees of freedom by 4, leaving 2. So the chi-square distribution that we have to compare this test statistic to has 2 degrees of freedom. Oh, that wasn't a very pretty one. I'm not really sure what it looks like, but something like this. So what we would do is that we would find out where is our test statistic here. What area does it exclude to the right? And that would be our p-value, telling us whether or not to reject the null hypothesis. If you think this way of finding the degrees of freedom is a little bit complicated, there's another formula which tells us that the number of degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So in our case, that would be, well, the number of rows of data here is 2. So 2 minus 1 times the number of columns of data, 1, 2, 3. We have 3. So that would be 3 minus 1. Whoops. I'll write it here, 3 minus 1. So altogether, 1 multiplied by 2, that gives us 2 degrees of freedom. So remember this formula here. So let's try to do this in Excel. So here we have the table of data corresponding to what we have here. And I'll start by computing the totals. I'll just make this shaded so that we know that no number is going to be there. Here we have the sum of those 3. We can copy that. And here we have total, the sum of those 2 here. Oh, something went wrong. Sum of, like that, and we copy that all the way over here. Right, and then we want to do the expected values. And I think that I'll just, well, we have to write the same things here. Oh. Like that. I'll just write those numbers here. You don't really have to do that, but I like to have the totals down here. Like that. I'll just make it shaded here. Like that. So the expected number here is then the number of men in total divided by the total number of observations multiplied by how many preferred candidate A. So you see you have this pattern here, same row, same column, and then the total, always the total. In this case we have total number of women divided by the total number of observations multiplied by the total number of voters for candidate A. And so you keep going. Of course, you can automatize this if you want to use Excel. You can copy this, but you would have to fix some of the columns and some of the rows when you copy the formula, and I don't think it's worth the hassle when we don't have more observations than this. But if you had a large body of data, then you certainly would try to automatize this procedure here. Right. So now I want to do the individual chi-square contributions, or terms in the sum if you like. Let's just remind ourselves what it looks like. I want to compute, we have 6 of these terms here, one for each cell, one for each expected value, you might say, or one for each observation. So I'll compute those 6 terms in the sum, arranging them in this table manner here. So the first chi-square number, or chi-square term, is the observed minus the expected squared divided by the expected. And then you can just copy this like that, and then you have the chi-square terms for each of these 6 cells here. And the actual chi-square test statistic is then the sum of those 6 numbers here. And there you have the number 6.658. The degrees of freedom is equal to 2 rows minus 1 times 3 columns minus 1, 2 degrees of freedom. And now we can compute the p-value. Oh, sorry. And that's 1 minus, because it's an upper tail test, so it's 1 minus the chi-square. I believe it's CHISQ in English. Here it's chi2 for dating in Danish. And you insert the test statistic, the number of degrees of freedom, and then you write true, or in Danish cent, to get the cumulative distribution. And we get a p-value of roughly 3.6%. That means if our level of significance is 5%, we can reject the null hypothesis. And let's just remind ourselves what that was. The null hypothesis was that there was no significant difference between the preferences of men and women. But we can reject that. At 5% significance level, we would say that there is a significant difference between the preferences of men and women.